Thank you. Thank you very much for the invitation to Alessandro and the other organizers of this school in bioresearch. And the technical problem was a crash accident in the highway, so that's why I'm a bit late, so sorry, I apologize for this. My name is Lorenzo MOJA. I'll speak about systematic reviews in animal studies, and I'll provide you an example, the case of statins. First of all, I am a physician. I study here in Italy, in Milan, but I did my residency in at the University of Ottawa in Canada. And actually, there are many passions in life. You may be passionate about flowers, cars, boats, whatever. I am passionate with systematic reviews and randomized trials. So that's one of my favorite topics. And rigorous research methodology. I am an editor for the Cochrane collaboration. I've been the vice director of the Italian Cochrane Center for several years. And I am a member of the grade group. So I'll also teach you on Friday, and we will cover both systematic reviews and then guidelines and applications of recommendations to policy and health decision making. So first of all, let me ask you something. How many of you works on basic science? Please raise your hand. Basic science, it means, you know, like animal studies or cell studies. Okay, and how many in clinical science? So on the 2, 3, 4. And so the other are here just by chance, or it's so substantially there are two main knowledge translation blocks. Okay, this is the basic biomedical research, and this is the clinical science and knowledge. Okay, so you may work on trying to transferring knowledge from basic science to human studies, and this is usually considered the first block, or you may work on the translation of clinical science to improving health, and in these cases you have classically the phase 3 trials, the registration trials, and what happens after that level, while phase 1 and phase 2 trials are in between. Okay, and nowadays these two blocks are almost equivalent. What it means that I expect usually in a room like this one to find 50% of the people working on this block and 50% of the people working on the following block. But this was not true 20 years ago. 20 years ago, it would be much different, the pictures in a room like this. Which block would have been the most prevalent 20 years ago? The first. Yes, it's true. That's correct. The first block, it would wait probably for 80% 20 years ago, while now they are well equivalent, okay? And I usually work on this block. So I try to work to transferring the evidence, okay, from randomized trials and systematic reviews to practice, okay? So that's where I work. But now I'm speaking about the first block, and I'll present you some of the shortcomings that we have in applying rigorous methods in animal studies. And I would like to start with this example. This is the Heart Failure University. It's exactly a meeting like this one, in which there are experts in cardiology meetings. And where do they meet, actually? In an airport. What's a wonderful venue. Okay, much better to be here in Varese, which is such as wonderful weather. Why they meet in an airport? Why would you meet with someone in an airport? I mean, there are no really basic reasons or good reasons to. Because the experts that go to these type of meetings, they are supposed to be busy, really, really busy, okay? So they don't want to travel, they don't want to be blocked on the highway, and so they prefer to just arrive in the airport and having there the meetings. But apart these is in this case, they are presenting these promising therapy for heart failures, okay? And this is important professor from the UCLA Division of Cardiology, okay, and he's going to present some important findings of a new drug, okay, that has been recently investigated, okay. So this is the results of the ENABLE trial, okay, and this is the new intervention, the new drug, Bosentan, okay, and the drug was compared to placebo in a classic phase 3 trial, okay, a registration trial to market then the drug which is Bosentan, okay, and these are the two hard endpoints, so death and CHF, cardio heart failure hospitalization, and all-cause mortality, okay, and these are the results. These are quite large trials, 1,600 patients. And would you say that these results are positive? Eh? Yes, to whom? Yeah, exactly. Are there any substantial difference between the placebo and the intervention? No. So how would you describe these results using just one term? Negative. Okay. The answer is incorrect. Why? Because negative, you would assume that the intervention is worse than the placebo, while the results now are inconclusive. So we cannot say that there is a superiority, okay. So negative is, but it's usually how we describe. So you use the common term, that's fine, okay. So these are like negative results, the p-value are all, okay, really far away from 0.05, okay, or they are close, in this case, even to 1, okay. So the difference that we have, they are all justified by chance variation, okay. That's how statisticians would describe the results. And here the problem is that why this drug has been studied in human. Maybe because it worked in animals. That's a good question. A good answer, sorry. So the question is now we will see if it works in animal or not. And how much the drug company has invested until now to arrive to this. How much does it cost one trial like this one? A lot, okay, good answer, a lot, but hundreds of millions. Okay, can we? Yeah, from the beginning, but the trial we can assume or presume somehow the cost for the patient. What would be the cost for the patient? Every patient randomized. Yeah. Per each patient that has been randomized. Yes. Yeah, that is, yeah, more or less would be, I would say something like this, okay? Then, when the drug companies present you the cost of the trials, how much would present? At least the double. Why? Why they present the double? So the cost would be 5,000. That would be a good cost for running a trial like this one, because the endpoints are big. Are they quick endpoints or not? Are quick in the mean? I mean, would you need some times to develop these endpoints or not? Yeah, sometimes, because you need to have, you know, death and then hospitalization, so you need time to get these type of events, okay? But why the drug companies that would charge, you know, like would say these trials costed twice what the real cost? because there is the marketing cost. Okay, and the marketing cost that apply, okay, after the drug has been discovered to be effective should then be charged on, usually are charged on the research enterprise. So you will see a huge amount of money that is translated from the marketing cost to the research development of drugs, okay? And this is a paper, okay, an editorial that asks, do results of the ENABLE study spell the end for non-selective endothelin antagonism in heart failure? So it's a title that kind of implies that the results of the trial were not really positive, okay? And this is actually what answers to your point. A meta-analysis of the effects of endothelin receptor blockade on survival in experimental heart failures, okay? And here what you have are preclinical studies, okay? So you would assume that the results in animals are clearly positive. They clearly indicate that the drug is superior to placebo. Mm-hmm. Okay. 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 But yeah, it's true. But if you are a drug company and you wanna beat your money on a drug, okay, then you would assume that the drug companies goes to see the animal studies before to launch a drug, before to launch a phase 3 trials, okay? We may be a bit naive, we may be, like a bit kind of doing some research that is not really useful, and we may use a few animals, but if you are a drug company and you have to put a bunch of money, then I would presume that the drug companies has a kind of, a structure, pipeline, and they go to the animal studies and they see what the animal studies say. Okay, and these are the 4 animal studies that were done before the phase 3 trials. Okay, so do you have any problems in reading the forest plot? Are you like familiar, or we should go quickly through the forest plot? Do you prefer that we kind of emphasize each aspect of the forest plot? Okay. Here you have the 5 studies. Okay, everyone is indicated by usually the first author and the year of the publication. Okay, and here you have the intervention and the control, and small and big, it means the number of events and the denominators of each arm, okay? So it means that the first study has 0 events, okay, out of 12 animals, okay? And in the control, it has 1 event out of 13 animals, and this is the relative risk. Here you have the measure of associations with the 95 confidence interval, and the same information is displayed here. Okay, here is displayed on numbers, here is graphically displayed, and then you go so on for every studies, okay? And here you have the total with the total number of animals and the total number of events for the intervention arm and for the control arm, okay? Now, let's look these 5 studies, okay? Every study that passes, okay, this line, This is the no difference line, okay, where the relative risk equals 1, okay? So because we are using 2 ratios, okay, and we divide then one by others. When we have 1, it means that they are perfectly equivalent. If they passes these lines, it means that the study is not significant, okay? And you can see that out of 5 trials, there is only 1 trials, okay, that stays on this side, okay, in which you have a difference between the intervention and the control group. Of course, it depends which is the outcomes. You can see that the outcomes is a benefit outcomes, okay? So here the intervention group has an advantage compared to the control, okay? So if you select only 1 studies out of these 5, and if you select these studies, you may think that the drug is a good drug, actually, okay? But this study has never been replicated by authors, and if you look at the overall analysis, this is the diamond, the meta-analysis. You clearly see that the confidence interval of the meta-analysis passes the 1 line, the no difference line, and so is not significant. There is a slight advantage for the intervention, around 40%, but is not clearly significant. And that would be a classic example in which to go or to not go in a phase 3 trials, you would probably not go, okay, in this case. And these are the results that were available before to have the registration trials that was done in 2004, okay? But no one did the meta-analysis of the animal studies. Actually, and this is a really good meta-analysis. Here you have the p-value of the overall meta-analysis, okay? So the test for overall effects, okay? This is the z-test results, and this is the p-value attached to these to the zeta curve, okay? And this is the test for heterogeneity. We may see then Friday something about heterogeneity, but this is a pretty good meta-analysis. All the results are ordered. You see that there are not much differences between one studies and the other. You have only 1 study that is significant, but overall we have a clear evidence that the drugs is not really convenient. It doesn't provide a substantial benefit. So it seems to not be the right things to go for a phase 3 trials, okay? And in summary, systematic and quantitative synthesis of preclinical pharmacological intervention studies may have utility in the assessments of novel therapeutic agents. In addition, quantitative analysis of results from multiple investigations may lead to estimates of overall effects, okay, which may differ substantially from the results of isolated small studies. Okay. Our results suggest that caution should be used against overinterpretation of small early studies of survival benefit. Do you think that now in 2014 the drug companies go for phase 3 trials doing meta-analysis, always doing meta-analysis? No. One recent case is the Ebola. Now the vaccines will be tested in humans, and there will be not preclinical studies, okay? There will be some background idea why the vaccination may be useful. So what are the reasons why drug companies may go on testing the drugs on humans without having strong backgrounds, strong preclinical data? Why that is possible? Yeah, in some cases they don't. Now there is some tension between the experts that they have for preclinical studies because they may argue one against the others. So they may pretend that one study is different for the others, but this one, let's say, big professors has the true answer, and so it's exactly like this case, if these studies, okay, which is slightly big, okay, compared to the first 3 others, if the experts that presents the results is really kind of credible, okay, accountable, it may then the drug go on humans. But there are other reasons, actually. There are other reasons that are that the drug companies has a pipeline, a structured pipeline, in which wants to push different drugs at different interval times, and these are related to the stock options of the holders of these stock options, and usually the money comes for a certain times because the drug are patent. Okay, so once you patent a drugs, then you have 20 years. And if you stay a lot of time in clinical studies, then what happens? That you are not taking advantage of the times in which you can push these drugs to humans. So there are like tensions because you always have research, markets, and these type of dimensions that can be sometimes conflictual. Okay, so I now go to the case of statins. These are the data that you will see are largely based in one big systematic reviews that we did with Professor Garattini, which is a well-known pharmacologist, and he is the director of the Mario Negri Institute. This is an institute that is considered, let's say, like quite high size institute, which has both basic research and clinical research. And Garattini has at the Mario Negri 15,000 animals are used every year. Okay, so 15,000. Is that a big number? Yeah, well, yeah, it's considered quite a large research centers. And when we spoke, he was really worried about the fact that the animal were not well used. So we were not taking advantage of the usage of these animals, and there were problems in the basic experiments that were run, okay, at his institute. So we needed to provide, okay, to the researchers of these institutes some feedback about the quality of the experiments. So there was a contingency to do this research that was basically really, really local. And then there is a message that may be of interest of also other researchers, okay? So the objective and the background, animal models and clinical trial studies are reported as effective, okay, in reducing the cholesterol. There are no doubts about these. So we took positive examples and lowering the risk of cardiovascular disease. We also know that the statins are useful in lowering cardiovascular diseases in humans. We exploring the differences in the efficacy of studies in 3 popular animal models. What it means popular, that these are the 3 animals models that are mostly used to study statins: mice, rats, rabbits, and we also explore whether the reporting, okay, of these studies was accurate, and we assess the risk of bias, so the bias assessments on the included studies. So from now on, for quite a few slides, I cover some methods, and then I go on the results of the meta-analysis, and then I go on deeply on the methods. I'm not a basic researcher, so I try to simplify for myself. Okay, that's my limit. Okay, so we use systematic reviews. Why? To summarize existing data, to understand the limitation of animal models, and to highlight differences between animal and human experimental procedures. And then, usually, in human studies, we want to help the design of new clinical trials that may be a bit different from animal studies. And here we have a classic systematic reviews. Now I'll give you some elements of the statistics. We are interested in the overall effects across all studies. So when we do systematic reviews and then the meta-analysis, we want to see the overall effects across all these studies. And in the case of statins, we are interested in the cholesterol, okay? Most of these animal studies, they look at the cholesterols and how statins reduce the cholesterol. This is a continuous outcome. It's not dichotomous. In human studies, we very often use dichotomous outcomes. In this case, we have total cholesterols, and so we have to use weighted and standardized mean difference, okay? Are you familiar with the continuous outcomes? And then it's the difference, okay, on a continuous outcomes, the difference in terms of total cholesterols, or it may be LDL, or it may be blood pressures, but all these outcomes are continuous. And we use a random effects meta-analysis, which is a type of statistical model to analyze the data that assume that there is heterogeneity among the studies, okay? We stratify by species, strains, and subgroups. We assess the heterogeneity by the I-squares, and we also assess the publication bias, which means that we want to know if all studies, okay, have been published, or maybe some studies have been conducted but then have not been submitted for publications by the authors, okay? So here we see, if we see whatever you use of these, we have the total cholesterols, okay, we will have the total cholesterols for the animals treated with the statins, the total cholesterols with the animal treated with the control, okay, and we should see a difference. If the difference is true, it means that these two populations, okay, are different and the p-value is significant. It may be standardized or weighted in the case of cholesterols, because all cholesterols are measured using milligram deciliters. It's fine. We can use the weighted mean difference. Then there is some statistical issues I'll speak about. Okay, this is the search strategy output. So we had Medline and Embase, okay, around a bit less than 2,000 records to be screened, and finally we stayed with around 120 studies included in the meta-analysis, okay? So this is quite a large meta-analysis, okay? This is the final number, 161, that's 100 studies analyzed, accounting for, and this is the important detail, 2,432 animals. Over how many years? Statins has been discovered when? In the 19th century, or maybe a bit later? A bit later, yes. So it's almost 20 years of research, okay? Is that a big number? Yes, sir? How? Yes, no, yes, not. How many humans have been randomized in statins studies in the same time? More or less than 1 million? 1 million. No, probably not 1 million, but probably between 100 and 200,000 have been randomized. Okay, so there is a huge, huge difference. But we say before that the same amount of money and resources go into the two blocks. But in one block, so this is the number that we have at the end, okay? These are the results, okay? So now what you are seeing is that every this point is not a single study, but is already the meta-analysis, okay? So what you have, you see the average effects in rats is minus 10%, in mice is minus 20%, and in rabbits is minus 30%. Okay, and here you have the different meta-analyses, okay, and when you see that the two lines are very, very large, it means that the confidence intervals are less precise. So here there is more imprecisions, and you see that for rabbits, for instance, the effects are largely imprecise, but they are huge, huge in terms of the benefits that we can see. So now from these slides, what seems to be the best animal model to study statins and to see difference between the statins and the control? Or let's say on another way, which is the model that seems to be the less appropriate? This one seems to be the less appropriate. Why? Yeah, it has the large confidence interval, but it also shows that with some model, there is a huge benefit, okay? And you also have to assume that the confidence intervals are derived by the total number of animals that have been used. So it means that here you see large benefits, but they use a small number of animals. Here, they use a large number of animals, okay? So basic researchers use a large numbers of animals, okay? But the effects are, so the results are pretty precise, but for most models, there are not clear differences between the statins and the control, okay? So if every animal has a cost, okay? And as a cost for the society, because we need to decide to sacrifice an animal, and we need to follow these animals, and if clearly we need a huge number of animals to see a difference, that seems to not be the well-performing model, okay? So somewhere here there are models that perform better, but are not very often used, okay? And these are the single meta-analyses. For instance, this is the Wistar Rats cholesterol reductions by study design, and you see that you have large differences between the studies. These are the randomized trials, and these are the controlled trials. So it means that here the authors are using a full randomization process to select the animals that go to the intervention, and the animal that go to the control. Here is not clear which kind of techniques that they are using. And you can see that here we have each line corresponds to one studies, and what you can see is this datum that is quite challenging. This is the heterogeneity. You assume that we are studying the same biological process, statins, okay, and the reduction of cholesterol. There may be so huge differences between these different studies, but look at these. The studies is clearly amazing. It only randomized how many animals? 10. And it has these precisions. How is that possible? How you can justify with a rational, a pathophysiological rational, these results? Also, this is pretty amazing. 6 and 6-12 animals, okay? This is a degree of precision. And this is, it's a bit larger, this study, okay? So it may be possible, but the results is amazing in terms of how effective are these statins. Or And maybe that these two authors, they studied the super settings, the super duper settings, okay, and nobody of the other had the same type of settings. But is that possible? Is that plausible? So what can be a rational cause of these two results? So the selection of rats, but here it's the same type. So we assume that these, I've been told that these animals are much more similar than humans, usually one between the others, because they are kind of genetically, some are genetically modified, they, like are inbreeded or whatever, and they, they come from the same families. So I would say that this is not like a strong explanation. What else? Selective, well, there may be something about the reporting. That's correct. Okay, I don't know if it's selective, because here they all provide the total cholesterol. So if you do an animal studies with statins, you always report the total cholesterols in the paper. So it's kind of, there may be some selective reporting too, it's true, but it may be in other outcomes. Usually the cholesterol is something that is always provided. So there are at least two reasons you may think immediately. Okay. One is that is an error. There is an error in the paper, okay, which is quite common. So they are reporting, the variability, and the variability is simply wrong, okay? Or there is some kind of scientific misconduct, okay? And it's not only from the authors, it's also from the peer reviewers. Actually, every peer reviewers that see a trial results, an animal studies with these results, should immediately reject the study. Should just say, it is impossible. Okay, this study is a study that should not go for publication for sure. There is something really that is, unless there is a strong explanation why these results was possible. So, and here you see that the heterogeneity goes up to 100%, which means that, okay, these results is almost impossible in human studies unless we are going to in psychology, where, like the variability is pretty high between one studies and another's. But if we study drugs and the effect that it has, usually these are like heterogeneity levels that cannot be seen in human studies. And you can see, in fact, that all the studies are spread. So studies are always good, but they are all spread, okay, between 0 and minus 100 milligrams for deciliters, okay? And always it's difficult to explain how you can have these results in animals, okay, over a period of few weeks, okay? This is a bit better. It's Wistar cholesterol reduction by diet, and so you see that now the studies have been grouped by standard diet or high cholesterol diet, okay? And also now you see that one of the two approaches seems better to study statins in animal studies. Which approach seems better? This is better. Here you see that the average reductions, it's quite small. So if you are interested in CN effects and then studies the effect that statins have on the infarct size, if you use these models, you can use less animal, you can see bigger effects, okay? You will be quicker in your studies, you will be more efficient, and substantially you will take advantage of a structures pipeline. If you use these animals, actually, which are many more, okay? Oh, well, yeah, many more, okay, you see by numbers, you will not fully take advantage of the different animal models, okay? And this is the LDL reduction. You see this is a very ordered meta-analysis. The heterogeneity is a bit less, okay? This is the only one with the high cholesterol diet. The effects is impressive. It may be possible, okay, it may be possible. These are not the case in which I would say that a peer reviewer should immediately reject the paper, okay? And these are other type of studies. Again, you see that very often there are studies that are somehow incredibly successful, okay? So these are all the results, okay? Now for blood pressure reduction and infarct size for each animal model and strain. And what I would like to show you here is that the blood pressure reduction and infarct size, these are two outcomes that are quite often used in human studies, but are by far less used in animal studies. So here you have only 165 animals that have been studied, and the outcome was infarct size. So most of the animal studies do not provide data on hard outcomes, on outcomes that are clearly relevant to clinical scientists. So it means that there is a complete mismatch between the basic and the clinical science. The two translational blocks, they don't speak one each other very, very well, okay? So these are the main results that I show you. Can I take another 15 minutes and you have a shorter break? Okay, thank you. So these are the judgments, and moving now on the method sections. Okay, these are the review author judgments about the risk of bias. Okay, this is the study design, the blinding, the extent of loss of follow-up, and the temperature control settings. Okay, study design, it means were these studies randomized, or the selection of the intervention and the control rats or animals were done on alternative ways, okay? And this is important fact, because with animal studies, it's pretty easy to randomize. It's pretty easy. So there should not be really some reason that prevent us to randomize. This is the blinding of researcher or data collectors, okay? This is the extent of loss of follow-up. What it means, that you can have also losses to follow-up in animal studies. What's an animal study that is lost? In some cases, I've been told that the experiments were not successful, the rats or the animal were not really compliant, and so it's lost somehow. Or it just died for like unknown reasons, okay? And then the temperature control setting, because I've been told that the temperature is very important, okay? And this is the same information on a table, okay? And some of these papers do not provide the number of animals that have been used. So when you think about the reporting of a papers, you do the experiments, and then you want to clearly say what happens in your experiments. And one of the basic information is to say, my study randomized 12 animals, 6 for the intervention and 6 for the control group. For some of these papers, it was impossible to get these informations, okay? And now you are seeing the meta-analysis of all studies, and you can really see how high is the variability, okay, between the different studies. All these studies have been ordered, okay, from the one with the most dramatic effect with the one, okay, that show an advantage for the control, okay. This is the overall meta-analysis, so you get a lot of precisions, okay. And now, this interval, okay, this interval show you not how precise is the meta-analysis, but where the next studies, the study that has not yet been done, can go, okay? So it can be here, 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 here. And so you see that for animal studies, the next studies is almost unpredictable. It can be in favor of the control, okay? It can be in favor of the statins, and we don't have a really clear idea. So what's the advantage in using this type of model to study statins? Is this a reliable model? Okay, this is with mice. Again, you have the same problems, okay, really large prediction interval. And this is for rabbits, is a bit better, but it's still, we have a lot of heterogeneity. If drug companies would see these results and then should decide to go or not to go to study statins in humans, it would be really an hard decision. Okay, so that's because the research, the basic research is not really structured around models, and has not really an adoption of methods that decrease the variability. Okay, and this is the funnel plot. Have you ever seen a funnel plot? How many of you have seen a funnel plot? Okay, so here you have the effect estimate. So the reduction in for cardiovascular risk, okay, in terms of cholesterols. And every of these one is a single study, okay? And here you have a standard error of the study. What is the standard error? It's a measure of the precision of the study, okay? And this area is the not significant area, while you see that the clear, the gray, the dark gray, or the light gray, it shows you the p-value, 1% to 5% and 5% to 10%, okay? So here you have the significant studies, okay? And we can assume, when you do an experiment, that half of the study, if you have a true value, a true effect size, okay, which may be in the case of the statins, a reduction for the cholesterols, half of the studies will be on the left side and half of the study will be on the right side of these two effects. So if the effects of statins, and we know that statins reduce the total cholesterol, if you say, okay, we'll reduce, okay, the cholesterol by 1 standard deviation, okay, this is the true effects, you will have half of the studies on one side and half of the studies on one side, okay? And the standard error show you how precise is the studies. So the bigger studies would be at the top. So because the studies that randomized or used most animals would be at the top. Why? Because they are more precise, okay? So they will be here, and because they are more precise, they will be very close to the parameter, okay, to the true cholesterol reductions. While the smaller one will be, you know, scattering on the bottom part of the graph, okay, and they should be both on the sides, so on the left and on the right side, okay. But here, what you see really a strange patterns of the studies, okay. So they accumulate somewhere here, okay. So it is presumably the true effect is -1 standard deviation, and then you have all these studies that are less precise and are only on the left side. What it means? It means that there is a selection of the animals and of the publication. Okay, so there is a strong pressures, okay, toward the researchers that probably select both the animals and then the publication to submit to journals. And here you have these incredible results of these few papers, which cannot be trusted, okay, because they are probably due to some kind of misconduct or frank errors, okay. These are all the funnel plot for every single species, okay, and they show almost the same. It's a bit different mice, but rabbits and rats, they show the same patterns with few studies always on the left bottom corner, okay. Now, let's see the comparison between basic research and human research, okay. Here you see the total number of animals that have been rats and mice, okay, excluding rabbits, the total animals that have been used in animal studies. And here you see the total number of humans that have been randomized in just one meta-analysis from the Cochrane library. So this is the 28,000 against less than 400 animals. Is this difference big? How is that possible to have this difference? I never found someone that is really able to explain me why it's so huge, this difference. It's a priori, there should not be such a big difference, okay? And this is then the problems with animal studies. So the majority of studies, they use a small number of animals. The power of the study is pretty small. And so this is the percentage of animals that you are wasting if you use this size of animals. But while you move to 32 animals, okay, so to a bit more than 30, then the studies start to be more useful, okay. This is to control for the infarct volume, so this would be a good animal studies with 32 animals going for an hard outcomes infarct size, and you see that the percentage of animals that can be wasted is pretty small. So the difference between 4 and 32 is now what we have, the gap that we should now try to fix, okay. This is the chance of wasting an animals in another way, okay, sure. And as you see that while you arrive to 30 animals, it's really then an animal study that it is worth. And so the difference, the problem is that right now probably we have most of the study that rely on this part of the curve. And so we see that the percentage of wasting the animal is pretty high. So are animal experiments falsely positive? My answer is yes. There often this is the case. They are many more times positives, while they should be probably less positive. Have animal trial tested the condition of maximum efficacies? Again, no, they do not take often advantage of the best animal models, and so the experiments are not so useful, are longer, and may provide not the right answers. And have animal studies consider appropriate models? Again, the answer is not. Okay, these are the two papers that we cover this morning, and as you see, the heterogeneity is usually very high. The results of the meta-analysis in animal studies for statins were difficult to interpret. So it means that also the meta-analysis for animal studies may be not really an easy approach. Different meta-analytic approach, and that is a bit more technical. Different meta-analytic approach gave us a very different effect size for reduction of total cholesterol. So it was kind of complex then to decide which one was the true effects. and policies that address these issues are required. And I don't know if the Scottish guy spoke about the ARRIVE guidelines or this new approach for animal studies. There are, do you know the PRISM or the consort statement? Have you ever heard about? These are guidelines for reporting. So when you present a trials to biomedical journals, the journal or a systematic reviews, the journal asks you if your papers comply with the PRISMA or with the consort guidelines. It means that you need to report these informations at this part of the papers. And now there is a guidelines also for animal studies that can be used to anticipate the type of information that the peer reviewers and the journal will ask you. Okay, and the name is the ARRIVE guidelines. Okay, and it's linked also to another papers that cover the methods. Okay, the methods of animal studies, and will improve your chance to get the paper published on high authoritative journals. Okay, so this is to see from another perspective, these are the press release annually released by an important research centers at Stanford. Okay, 44% promote animal or laboratory research. Okay, and 74, these 44, explicitly claim relevance to human health. Okay, while the other half, they are about primary human research. Okay, and these are all the omissions, okay, of the press release. Okay. And what you see that only 70, so only a small proportions of these press releases are promoted through studies with the stronger design, so they use randomized trials or meta-analyses, and 40% report the results of weak design, uncontrolled studies, small samples, surrogate primary outcomes. And the conclusion is that the press releases from academic medical centers often promote research that has uncertain relevance to human health and do not provide key facts or acknowledge important limitation of the studies. Why? Because researchers are still good in presenting their results to the press offices. Okay, they are not maybe really good in, like using robust methods. And do it right, please. Thank you very much for your attention.